Hello everybody and welcome back to this final day of the UK PONI 2021 Annual Conference. I hope you've all had a fantastic time so far. We've just got the one more panel to go before we have our exercise later on today, and it promises to be a really interesting one as well. Congratulations as well to all of those speakers who've come before. You've done a fantastic job. I've learned a lot already, and it's been really interesting listening to all of the thoughts of the emerging scholars and professionals that we have here. For those of you who didn't pick up over the last couple of days, my name's Tom Plant, Director of Proliferation and Nuclear Policy at the Royal United Services Institute, and I'm also the Director of the UK Project on Nuclear Issues. So tremendous privilege to be involved in this as ever. So this session is going to be a little shorter than some of the other ones. We have a couple of fantastic presentations lined up on some of the more technical issues, one of which was completely out of the range of things that we thought we were going to be expecting. I didn't think we were going to go to Mars at any point during this conference, but it turns out that we might with the aid of nuclear propulsion. So we'll see how we go. One thing that I will say at this point, normally we wouldn't want to run a male-only panel at a RUSI conference, at a UK PONI conference. And so one thing I'd like to do is point out two things. In the resources, you'll have seen the UK PONI approach to diversity in the way that we've approached constructing this conference and across our program in general. Feel free to check that out and have a look. As ever, we're open to suggestions for improving the way that we do things. We are moving beyond gender, of course, to look at other forms of diversity as well in our programming. And the second thing I'd note is that this is, one of the teams here is actually a mixed gender team. It just so happens that we have a male representative speaking. So in those cases, please feel free to check out the resources and see what you think about how we've done on that issue across the conference as a whole. But onto this panel itself, we've got two great speakers, both on graduate training schemes, actually, as it happens. Or I think Sam may have just come off, I can't remember exactly. Bhaumik is on the AWE graduate scheme. He's a warhead systems engineer. Very interesting technical background, but has developed an interest in international diplomacy, policy, nuclear non-proliferation, all that, as all good technical people should. So congratulations, Bhaumik. I appreciate that. And then Sam, of course, with a joint Lockheed Martin and Rolls-Royce team. I won't go through all of the bios because it will take quite a long time, but including past speakers as well, and some people who are new to working on UK PONI. So Sam, it's a delight to have you with us. Really looking forward to your presentation later on. Okay, so let's pitch right into it. Bhaumik, let's hand over to you and talk to us about thorium fuels, widely touted as being proliferation proof, but are they really? Over to you.
Thanks for that, Tom. Just a quick one. I have completed my graduate scheme now. Thanks for the introduction. As Tom suggested, I'm going to be talking about thorium, nuclear fuel more specifically, and exploring whether they really are proliferation proof. Before going to my presentation, just a quick disclaimer: all the views presented in this presentation are my own. I do not represent views of the AWE, MOD, or the UK government. So thorium, the wonder fuel, is often described as that in the media. My interest in thorium started when I watched some TED Talks, specifically talking about the thorium nuclear power, and I thought to myself, that seems too good to be true. And you would often hear or read the headlines, for example, is thorium the answer to our energy crisis? You'd quite often read sections such as, it could power the planet for thousands of years, the reactor would never blow up, and the waste is relatively clean. Thorium is safe nuclear power. So that is correct, but I also think that that's not the whole picture, and I suppose the aim of this presentation is to explore that. So why thorium? Why is there interest in thorium? And quite a lot of people are talking about thorium. So one of the main arguments is that the thorium itself is more than 3 times as abundant as uranium. But is that an issue right now? Are we running off uranium? No, probably not. But as you can see from the world population growth and projections, that the population is keep going to rising, which means our energy demand is going to increase significantly in the future. Therefore, we need to start thinking about alternative energy sources, and thorium is the prime candidate for that. On the table on the right, it just shows the thorium resources as of 2016. And India, Brazil, Australia are some of the countries with the most thorium resources. Second argument for thorium is the fact that the extraction of thorium-232. So the thorium-232 is what's actually used in the nuclear fuel. And so this is massive take in terms of economics. Economically, is a great material because we do not have to do too much refining when you mine for thorium. You can essentially use this material and put that straight into the reactors. Third point is probably the most important one in terms of why thorium. So with regards to reactor designs, thorium itself is very fertile, which means you can easily modify some of our current reactor designs to use the thorium as a fuel. Did I stop presenting by any chance? Oh, there we go. Sorry about that. So with regards to nuclear waste, that's a really massive advantage that thorium has over uranium nuclear fuel. The nuclear waste that you get from uranium, you'd have to store it for hundreds and thousands of years, whereas the nuclear waste generated from the thorium, you only have to store it for hundreds of years, which we know how to do that. We already have process and procedures how to store something for hundreds of years. Risk and safety. I suppose this point and the point I'm going to be talking about next, it kind of applies for the whole nuclear energy, not just for thorium fuel. The nuclear energy has the persona of being really dangerous and really deadly, but that's not the case. If you look at the numbers, if you look at the deaths per 1,000 terawatt-hour by different energy sources, nuclear is way less compared to oil, coal, or natural gas, or even hydro, wind, and solars. And lastly, it helps tackle the climate change. Again, if you look at the numbers of carbon dioxide produced per kilowatt hour of an energy, the nuclear power is as clean as the wind turbines. And the energy produced from the nuclear power is far more compared to all the other energy sources combined. So that's great. Thorium is great. There's also the argument for the non-proliferation, the proliferation resistance as well. So what are these arguments? The one of the first being is that thorium itself is not fissile. Fissile meaning the material itself can't contain the chain reaction required to produce energy, release energy, which means someone can't just steal a bunch of thorium and put it together and use it as a nuclear weapon. So that's a great argument. But the question is, how does it produce energy if it's not fissile? So the nuclear fuel, thorium nuclear fuel cycle involves converting thorium into uranium-233, as you can see that in the equation there. The reason why I've highlighted uranium-233 and throughout this presentation, I have highlighted things red just to emphasize that material is fissile and it can be used for the nuclear weapons or potential devices. So that's great. You can't steal thorium to use it as a weapon. What about the spent fuel? It's very difficult to extract the uranium-233 from the spent fuel. It would require large infrastructures, which becomes very hard to grade argument why thorium is really good. And lastly, the existence of uranium-232. The important thing you need to remember here, I'm not going to detail how you can get uranium-232, but the important thing to note is that whenever you do use thorium fuel, you would create uranium-232. When you use thorium fuel, you would create uranium-232. The reason why this is good and for the proliferation resistance argument is that the uranium-232 is really highly radioactive, which means it becomes very easy to monitor the spent fuel. Okay, For some reason, my slideshows keep stopping. All right. There we go. So that's the argument for the proliferation resistance. The fact that you can't use the material itself. It's very difficult to extract uranium-232, and the existence of uranium-232, which becomes very easy to monitor the fuel. So what are the concerns? The concern is described in Ashley's paper. It is possible to extract protactinium-233 rather than uranium-233. So as I suggested earlier previously, it's very difficult to extract uranium-233. But in this, you can chemically extract protactinium-233 using your standard lab equipments, which are not necessarily subject to IAEA safeguards. There are two methods which can be used to chemically extract protactinium-233, which will leave you with pure uranium-233, the fissile material which can be used in the nuclear weapons. I'm not going to go into technical details as to how these techniques works, but one of the key things to remember is the fact that both of these chemical methods are tried and tested. It's fairly well designed. The science behind is well understood, and it currently is being used in a number of chemical procedures in the nuclear industry. And there's evidence of US using acid media technique to produce more than 2 tons of pure uranium-233 during Cold War. So, okay, we got uranium-233. What is the concern? Just to emphasize again, is fissile material. A number of countries such as the US and India have tested uranium-233 based devices. US did their test in 1950s in Operation Teapot, and India did their test in late 1990s called Operation Shakti. IAEA categorizes uranium-233 in the same category as HEU, highly enriched uranium. And the significant quantity defined by IAEA for uranium-233 is 8 kg compared to 32 kg for HEU. Now, what does that mean? This basically means that you do not require as much material to create a weapon using uranium-233. And lastly, in the paper produced by Ashley, he states that using one of those chemical techniques mentioned in the previous slide is feasible to obtain that significant quantity material in less than a year, which is quite worrying. And it's really surprising that all this kind of things has been discussed in the media and on the other side. So to conclude my argument, is thorium proliferation proof? No, thorium is not proliferation proof, and we need to change our language when we talk about thorium. Thorium fuel has clear advantages over uranium-based fuel, that is granted, but in terms of proliferation risk, I don't believe we necessarily understand the risk when we talk about thorium. The greater debate and research is required to understand that proliferation risk. And lastly, proliferation is a political issue. Therefore, it needs to have a political solution. Almost all nuclear technology is a proliferation risk, and the state will proliferate out of political necessity and imperatives, regardless of their capability or infrastructure. Thank you for listening.
Great. Thank you very much, Bhaumik. Really appreciate that, and well fought through the connection difficulties. You've done a really good job there, and thanks also to the event staff for jumping in and helping share the presentation. I thought that was super interesting because I've heard many times, you know, thorium, as you said, touted as sort of this almost kind of wonder solution to the proliferation challenge. And as you say, the devil is always in the details, and that 2012 paper is really quite scathing in some ways. So anyway, let's go into more of that and maybe some of the geopolitics later on, because of course where thorium is also becomes important, doesn't it? So let's talk about that in a bit. But before we do that, let's go over to Sam Brass or Brass, depending on whether you're northern or southern, you can tell me, from Lockheed Martin, representing a joint team, a fantastic piece of joint work on on human spaceflight to Mars, or indeed, any other kind of spaceflight to Mars, potentially nuclear powered. So Sam, take it away.
Thanks, Tom. Hopefully everyone can hear me now. Yeah, so as Tom said, I'm going to be talking about nuclear propulsion in the UK, trying to answer the question, can the UK accelerate humans towards colonizing Mars? So obviously this is a joint Lockheed Martin, Rolls-Royce research area. So I've got all the names of the people, all the contributors on the slide there. Many of them are listening in today, so thanks for all your help. So just a quick disclaimer. The views and opinions expressed here are those of the authors and in no way represent the views, position, or opinions expressed or implied of my employer or anyone else. So why do we actually care about nuclear propulsion? Well, it's been on NASA's radar for around 60 years. And this culminated in what was called the NERVA program, where they produced a rocket powered by a nuclear reactor and performed around 20 ground tests of this type of propulsion. This was around in the 60s and 70s. But more recently, NASA has published a request for technology concepts to industry. And this happened around 2 or 3 months ago, where they're looking into different types of nuclear propulsion and how they can be used in the future. Elsewhere in the world, China have announced that they are planning a nuclear-powered space shuttle in 2045 for various different applications. And also in the UK, Rolls-Royce and the UK Space Agency have recently joined forces in a study to pave the way for how the UK can tap into this market and exploit its benefits. So the purpose of this study was to perform an investigation into the benefits of a UK-designed nuclear propulsion system for future cargo and manned missions to Mars. The mission profile we were looking at were launch dates in the mid to late 2030s, and the data that we'd be comparing would be a quantitative comparison between conventional chemical propulsion systems and nuclear propulsion systems. And the main two pieces of data we're comparing is the payload to surface, which we'd obviously like to maximize, mainly for the cargo missions, sending all the important equipment that we need before we actually send humans there, and minimizing transfer time. And this is more important for the manned missions, where we want to minimize the crew and the passengers' exposure to harmful cosmic radiation and the effects of microgravity. So the next few slides, I'm just going to go through different types of propulsion systems and explain sort of how they work and the pros and cons of each. So starting with conventional chemical propulsion systems, the way that these work is you have a fuel tank and an oxidizer tank, typically oxygen, and you pass these through pipeworks, compressors, turbines, and things like that into a combustion chamber, where you then ignite it. There's a chemical reaction which releases heat, and then you expand those hot gases through a converging diverging nozzle, which generates thrust. So benefits of this is you get high thrust at both sea level here on Earth and also in a vacuum. So depending on the configuration of your nozzle, you can make high efficiency, high thrust in all sort of profiles that you need to perform space travel. Additionally, the fuels are easily manufactured both on Earth and Mars. So for this SpaceX Starship example, they use methane and oxygen, which is very easily manufactured from ice and carbon dioxide, which is both abundant on Earth and on Mars. The downside is obviously we're traveling in a vacuum for most of the time, so we need to take our own oxygen with us. And typically, you have 6 times as much oxygen as fuel. So this is a massive mass hindrance, which means it takes away from your useful payload that you can transport to Mars. So recently, SpaceX has won a contract from NASA to build a lunar lander for the Artemis missions, which is the next missions for humans to return to Mars. And this is worth almost $3 billion. So there is a lot of big money in deep space travel. So what's the difference with nuclear thermal propulsion systems? So here we are replacing our chemical reaction that happens between fuel and oxygen with a physical heat exchanger. So basically we use our nuclear fuel source, nuclear reactor, pass our propellant through, typically low mass gases such as hydrogen or helium, through the nuclear reactor, which acts as a heat exchanger, passes the heat into the gases, which are then expanded through a nozzle similar to the chemical propulsion system. And with these systems, we get around twice the propulsive efficiency as you get from chemical, but you get comparable thrust. Additional benefit, obviously, we don't need to bring the oxidizer with us, so we get a significant mass saving. However, one downside is the reactors run at extremely high temperatures for long periods of time. So we obviously need to work out how to cool these kinds of systems, which requires quite large arrays of radiators. So another recent contract that was given by NASA, or by DARPA in this case, was to Blue Origin, General Atomic, and Lockheed Martin in the US, who are producing a similar technology demonstrator as the NERVA program, and are hoping to test this by 2025. It's worth around 27 million, but this as an early stage project could lead to much larger contracts in the future. So finally, nuclear electric propulsion. So here we're using our nuclear reactor as an electron generator, and we're passing the electrons through what's called an electron gun. And this impact, the electrons fired from there, impact with the propellant, which is typically a noble gas such as xenon or krypton. And that produces a positively charged ion, which can then be accelerated through positive, negative grids to accelerate the propellant and produce thrust. So here we get up to an order of magnitude more propulsive efficiency than chemical. We've got few moving parts, so that's good from a mechanical design perspective, much more simple than the previous two. And we get reactor uses on Mars. So because our reactor is producing electricity, once we actually get to Mars, we can use that for producing useful energy on our Martian base. One major downside is that the flow rates through the engine are quite low, which means that we produce low thrust. So this means it's only really suitable for vacuum between Earth and Mars, not for launching or escaping Earth gravity field, for example. So these typically have to be combined with other types of propulsion systems. And there's another example from Ad Astra of a contract they've recently won. So as I mentioned earlier, Rolls-Royce are producing some kind of case study with the UK Space Agency on how the UK can exploit these technologies. They've been investigating these types of nuclear reactors since the 1980s. And the paper that they've recently produced, it's not in the public domain, but here are some typical kind of values that they're aiming for reactor designs in this kind of domain. And these are the kind of inputs that we've been putting into our models to simulate these kinds of trajectories. So moving into the analysis side of the study, we decided on using SpaceX Starship as a conventional case study that we would then base all of our assumptions and future studies for nuclear propulsion on. So talking through their mission profile to Mars, they start off at step 1 with their SpaceX strapped to a booster on Earth. They launch their Starship into Earth orbit. And once it's in Earth orbit, they then launch up to 4 tankers, which then perform in-orbit refueling of the Starship to refuel the fuel tanks. Once that's done, the Starship burns its engines again and escapes Earth's gravity field into step 4, transporting it towards Mars. And this is the section we're mostly interested in, because this is the long duration section of the mission and where we can see the most benefits from a nuclear perspective. Once we get to step 5, the Starship will arrive at Mars and enter its atmosphere, land on the surface, perform their mission, in which they will perform in situ propellant production, as I alluded to earlier, and then they'll perform their return leg. So typical quoted values from SpaceX on these types of missions. For a cargo mission, they're aiming to transport around 200 tons to Martian surface. And for a human mission, they're aiming to eventually get up to 100 or more passengers per mission. So into the analysis side of things. So the team at Lockheed used open source mission software called GMAT. And the idea was to use that conventional Starship step 4, the interplanetary trajectory, and compare that to a nuclear thermal system with a Rolls-Royce nuclear reactor. So the diagram there just shows the sun in the center, and then we've got the inner orbit is the Earth's orbit, And then finally, the outer orbit is the Martian orbit. So we're going from step 1, where we leave the Earth's gravity well in our single maneuver called a transorbital insertion. We go to step 2 into our transfer orbit. This typically takes around 6 months to complete. And then we perform a second maneuver called a Mars orbital insertion once we get to there. So a few critical assumptions we've made. We're only looking at a one-way interplanetary trajectory. We're not interested in the return leg, but it will largely have the same kind of implications. We've assumed a consistent spacecraft dry mass, but we appreciate there'll be a shape difference in the conventional versus nuclear. And we've assumed impulsive maneuvers. So impulsive maneuvers basically means you can burn your engines because we're burning for a comparatively low amount of time, typically seconds in our maneuvers, compared to the overall trajectory, which takes months. We're assuming that these maneuvers are instantaneous, so we get an instantaneous change in velocity as a result. So in terms of working out the timings of all of these missions, we've looked at 2 sources, one being NASA's design reference architecture, and also NASA's online trajectory browser. So collating inputs from both of those sources, we've arrived at a cargo mission departure of 2035 and a crewed mission departure of 2037. So for the cargo mission, we have taken the top right diagram, which is a kind of cross-section of the Starship system. And we've said, okay, between our conventional and our nuclear thermal case, we are assuming the kind of skeleton, the structure is the same mass between 2 systems. So our dry mass is 150 tons. And then we are filling our fuel tanks with conventional fuel, which is around 1,100 tons. And for the nuclear thermal case, we're filling it with liquid hydrogen, which is a typical fuel for nuclear thermal engines. And that gets you to around 290 tons. We then perform our 2 maneuvers at Earth and at Mars. And we have a 10% fuel remaining just as a safety factor in case we need to do any orbital adjustments midway through or towards the end. And we arrive at a comparison of around a 19% saving in payload for the nuclear thermal case with these parameters. So a pretty significant increase, which will obviously get you more useful equipment onto the Martian surface before you send humans there. So looking at the crewed mission, the difference with this is we're trying to minimize our transfer time just for crew benefits and things like that. So here we've got the same assumption. We're assuming a dry mass between both systems. But this time we are saying, okay, we'll transport 100 passengers between each one. We'll have the same amount of fuel, but what we'll do instead is calculate the maximum amount of velocity we can get from burning that fuel. And the difference is reasonably significant there, with around a 17% decrease in transfer time between conventional and nuclear thermal. So this slide just shows an image of how the trajectories differ. So on the left, we've got conventional, 192 days, and on the right, we have nuclear thermal. So as you can see with the nuclear thermal, it's a much more aggressive trajectory. We're increasing our radius much faster. And this is because we can burn a lot more and we can generate a lot more velocity out of our fuel. So a bit of future work. So obviously with this short study, these were very top level transfer trajectories. There's a much more in-depth analysis that you would typically do if you were actually planning a mission like this, which require many different parameters to optimize and requires a lot more computing power and setting up the models and things like that. Additionally, we assumed only 3 bodies in the solar system, the Sun, the Earth, and Mars. But perturbations or changes in the trajectory from other planets are non-trivial. So ideally, you'd include that as well. And again, nuclear electric, we haven't actually touched on this in terms of analysis. And the reason for this is because the impulsive maneuver that I mentioned earlier is unsuitable, because typically you would burn your nuclear electric engines for in the order of weeks to months, which is comparable to the length of the journey. So in terms of the analysis in this, it's invalid. And also, obviously, like I mentioned earlier, you need typically hybrid propulsion systems, which very much complicate the analysis phase. But what we have done is looked at the amount of fuel that you could get if you were to perform this in a nuclear electric. And we've compared the specific impulse, which is a measure of how efficient the system is. And typically you get around 10 times the efficiency of conventional. And when you combine all of that together, you get a maximum change in velocity of around 4 times of what you get in conventional. So we're estimating if you were to be able to perform one of these complex analysis, you'll get a significant benefit from nuclear electric. So in conclusion, in answering the question, can the UK help to accelerate the colonization of Mars in both cargo and manned missions? I think the answer is yes. With nuclear electric, it's worth investigating further in a more in-depth analysis. But yeah, that's pretty much it. So thanks everyone. I look forward to your questions.